Open up your workbooks to page 67, and let's take a look at problem number 2 today for our warm-up. Problem number 2 asks you to create a second equation so that you are creating a system that has no solutions. Let's think back to one of our previous lessons where we looked at graphs of equations with no solutions. We learned the other day that if the two graphs have no solutions, their lines would run parallel. So when working with parallel lines, that means our rate of change or our slopes would be the exact same. So you can come up with any equation here with the same slope, but just different y-intercepts or initial values. So I can come up with any equation with a slope of 3/4 and something different other than -4. For example, I might do y equals 3/4 x plus 8. I know when I graph these two, they will be starting in different locations. The top one will be starting at -4, and the bottom one will be starting from 8 on the y-axis. But they will both be going up 3 and over 4, resulting in two sets of parallel lines. So as long as you've come up with an equation with a different initial value and the same slopes or rates of change, your system would work and it would have no solution. We can then prove this algebraically. If we take what y equals in the top equation, which is 3/4 x minus 4, and set it equal to what y equals in the bottom equation, which minus 3/4 x plus 8, and attempt to solve for x, watch and see what happens. If I want to combine terms with x's, I would go ahead and subtract 3/4 x from both sides. Sorry, that's should be 3/4 x minus 3/4 x minus 4 equals 3/4 x minus 3/4 x, because remember, plus 8, whatever you do to one side of the equation, you must also do to the other. And when I take away 3/4 x from both sides, I get a 0 pair. Notice what I'm left with. -4 equals 8. Is that a true statement? Absolutely not. -4 will never be equivalent to 8. So because we get these two unequivalent numbers in the end, it's proving how these two equations would result in no solution when graphed or when thought about as a system of equations. All right, once you have your work for your warm-up, let's go ahead and move on and take a look at today's lesson. Feel free to pause the video if you need to copy anything down. Today, in lesson 13, we will be able to connect features of graphs to the number of solutions a system could have. We will be able to solve systems algebraically, and we will be able to see and describe the structure and systems of equations. More specifically, you should be able to walk out of the door today being able to solve systems of equations using algebra, like we just did in the warm-up, and graphing the system of equations and identifying their solutions like we've been doing the past several lessons. Let's get started on your first introduction activity on the top of page 69 in your workbook. So please join me on page 69. In this problem, they're asking us to think about whether the 5 statements below are true or false, and use the graph to do so. So at this time, why don't you go ahead and pause the video and see if you can figure out if statements 1 through 5 are true or false, and then you can go ahead and press play, resume, and check your work with mine. All right, problem 1 says a solution to 8 equals -x plus 10 is 2. So if I take a look at this equation, 8 equals -x plus 10, they are referring to the line up here where it says y equals -x plus 10. What they are telling me is that y is 8 and x is 2. So if I were to think about that in terms of an ordered pair, that would be 2, 8. So I'm going to ask myself, does 2, 8 fall on this line? So if I go right 2 and up 8, it does in fact fall on the line. So if we input 2 as x, we do get an output of 8 for our y. So for question 1, I could say this holds true because 2, 8 falls on the line of y equals negative x plus 10. If you did not have that for question 1, go ahead and add it to your notes now. Let's take a look at question 2. Question 2 says, is 8 a solution to 2 equals 2x plus 4? I see that they are looking at 2x plus 4, so that draws my attention to the other line being represented as y equals 2x plus 4. If I were to interpret what they're saying down here, if you notice, they replaced the y with 2, and they're saying now let x be 8. So is this a true statement? Does 8, 2 fall on this line? Well, let's take a look. Now again, we're referring to the other line over here, the blue line, I just drew it. If I go right 8 and up 2, am I on the blue line? No, I am not. I'm actually on the first line, the red line. So, is 8, 2 a solution to y equals 2x plus 4? That is in fact false. And for the very same reason as above, because 8, 2 does not fall on the line y equals 2x plus 4. So we can add that in false because 8, 2 does not fall on the line of y equals 2x plus 4. Now that you have maybe a better idea of what they're looking for, if you haven't tried one on your own, see if you can attempt problems 3 and 4 on your own. Press pause and then check your work with mine. All right, let's take a look at question 3. So question 3 now is asking, is 8 a solution to both negative x plus 10 and 2x plus 4? Since they set the two equations equal to each other, that means it must hold true. X must be 8 for both. So let's take a look at that concept. If I look at when x is 8, we said that holds true on one line, but that doesn't hold true for the blue line. So for question 3, I would have to say that it's false. In order to find a point that holds true for both lines, we should be looking for the point of intersection, which this point here clearly is not. So here I'd have to say false, because when y is 8, or excuse me, not y, when x is 8, it is not the point of intersection. And it needs to be the point of intersection in order to be a solution to this equation or to this system of equations. Now they ask in question 4, is 2 a solution to the following equation? Negative x plus 10 equals 2x plus 4. So again, they took the two equations from our system and set them equal to each other. So again, that tells me they're looking for the intersecting point, which would make both equations true in the system. This is representing x. So is that true if I look back up at the graph? When I go over 2, I do hit the point of intersection for both. It falls on both lines. So I would say true for the fourth statement because x is 2 for both equations in the system, and it is the point of intersection. Remember, we can also check that algebraically. If I input 2 to this equation, it should work. So is negative 2 plus 10 equal to 2 times 2 plus 4? Well, negative 2 plus 10 is 8. On the right side, 2 times 2 is 4, and 4 plus 4 is 8. So it works, okay? You can do that same thing back in question 3 and prove question 3 to be false. If I were to input 8 for x algebraically, is negative 8 plus 10 equal to 2 times 8 plus 4? Well, negative 8 plus 10 is 2, right? 2 times 8 is 16 plus 4, and 16 plus 4 is clearly not 2, but rather it is 20. So those two are not equivalent. So algebraically, that's how we can prove that. All right, let's take a look at question 5. Again, please make sure you have all this written in your notes. If you need to pause, go ahead and do so before continuing with problem 5. There are no values of x and y that make y equals negative x plus 10 and y equals 2x plus 4 true at the same time. Well, we've already talked about why this statement would be false, because we found a point of intersection for these two equations or these two lines. So since we have a point of intersection here, that clearly is the solution to both equations. So for number 5, we would have to say their statement is false because there is a point of intersection located at, sorry, let me go back up, why not 2, 8. So therefore, that is the solution that makes both equations true. Both equations in the system. We could also check that algebraically, just as we did the previous two problems. If I let x be 2 in each of these equations, I should get an output for y as 8. So if I check y equals negative x plus 10, and I replace y with 8, and x with 2, it works for the first equation because I know negative 2 plus 10 does in fact give me 8. Not only does it have to work for the first equation, but it also has to work for our second equation of y equals 2x plus 4. Again, if we replace y with 8 from the ordered pair and x with 2, we should get a true statement. 2 times 2 is 4. 4 plus 4 is 8. So it does work for both. So that algebraically further proves by checking the coordinate that it truly is a solution for both equations in the system. So their statement that they made was false. Please make sure you have all these notes jotted down. If you need to press pause, go ahead and do so. And get everything in your notes. If you have everything, let's go onward. All right, so as I had stated, please make sure that you've checked all your solutions with mine and added any additional things you needed in your notes. If we take a look at the equation given to us, which was given to us back in problems 3 and 4, and they say to now check it even further and confirm that x is 2 by solving it algebraically. So let's think about how we can do this. Hopefully you have some room at the bottom of page 69 where you can solve this equation algebraically. So go ahead and jot this equation down in your notes. Negative x plus 10 equals 2x plus 4. So if we want to solve this equation using inverse operations, we'd probably want to combine our x's together. I'm going to do so by doing the inverse of a negative x. So I'm going to add x to both sides. Whatever I do to the left, remember I have to do to the right to balance out my equation. Negative x and positive x give us that zero pair on the left. 2x plus 1x gives us 3x on the right, plus 4. And then I am going to go ahead and subtract 4 from both sides. So I can combine my 4 with my 10 and do the inverse of a positive 4, which is a negative 4, or subtracting 4, right? So I get my zero pair on the right. On the left, I know that 10 minus 4 gives me 6. So now I'm left with 6 equals 3x. And my last inverse operation would be to divide by 3. And I know when I divide 6 by 3, I do in fact get 2. Which confirms that x does in fact equal 2. And when we go back to our graph, remember that x coordinate was 2. So please make sure you have this work solved algebraically somewhere at the bottom of page 69, squeezed in there hopefully, or even in the top corner of page 69, you may have a little room to work. So pause the video now if you need to make sure you have all the appropriate work shown and the confirmation that x is 2. Then we can go on. All right, let's take a look at the next activity in your workbook on page 70. So join me on page 70. For this task, they are asking you to take a look at the 3 graphs, at the 3 systems of equations graphed, and match each of the equations below with each of the graphs. So think about your slopes, your y-intercepts, and how you can match those figures with each graph. So go ahead and pause the video now. Do your best to match the graphs with the systems, and then you can check your work with mine. All right, let's see how you did. If I were to start with system A, it says y equals 3x plus 5, and y equals negative 2x plus 20. When I look at that system, I can notice something that's pretty clear right off the bat. I notice that I have a positive slope and a negative slope. We did an activity similar to this several days back where people noticed these things. So you don't even have to get crazy detailed if you're noticing these smaller details. So if I have a positive slope of 3 and a negative slope of 2, which of these graphs have both a positive slope and a negative slope? Well, I can eliminate B because both slopes are going up from left to right. I can also eliminate C because, again, both slopes are going up from left to right. Sorry, my calibration must be off. So that leaves me with choice A, which I have a positive slope here and a negative slope here. I can also further confirm that graph A should match with system A by looking at our vertical intercepts, or our y-intercepts. This y-intercept is at 5 for my positive slope. Notice the y-intercept is at 5 for my positive slope. This y-intercept is at 20 for my negative slope, and notice the y-intercept is at 20 for our negative slope. So I can match A with A. Let's take a look at system B. If I go with that same thinking and compare their slopes, both are positive, which they should be because we know, we just discussed that both graphs C and D have all positive slopes. So now I have to dive deeper into their y-intercepts. So the first one has a y-intercept of negative 10. So I can eliminate graph B because if I go down to negative 10, there's no y-intercept there for either of our lines. So graph B is out of the question, so it's got to be C. Let's double check and confirm. I do have a y-intercept at negative 10, and then I have a second y-intercept at negative 1, And there it is. It's hard to see because they're counted by fives, but it's there. So that further confirms that system B goes with graph C. So last but not least, that should mean graph B should go with system C. So let's confirm that graph B goes with system C. Again, with that same notion, if I compare my y-intercepts, the first one is at plus 12. So if I go up 12, I see a y-intercept there. My second equation in the system is at plus 27, and it looks like that y-intercept is right there at 27. So that further confirms that graph B pairs up with system C. So please make sure you have the correct matches, and hopefully now you have that little bit stronger understanding. Look for those slopes, positive versus negatives, and then if that doesn't eliminate things, go on to their y-intercepts and see where they're located on the graph and compare them with your systems of equations. All right, so now for part 2, it says find the solution to each system and check that your solution is reasonable based on the graph. So they don't want you to actually use the graph for your solution. They want us to actually think of another way to find the solution. Well, we know another way. We can do it algebraically. And in fact, you've been solving equations algebraically for quite some time now. We just need to think about how we can relate this now to the system and make the two equations one to solve it algebraically. So let's go ahead and do that now. You have plenty of space on page 70 to show your work. Oops, sorry. Okay. So if we take a look at system A, I know that I can just take what the top equation equals, 3x plus 5, and set it equal to what the bottom equation is set equal to, negative 2x plus 20, and solve that equation for x. So let's go ahead and get started on solving this equation for x for system A. Remember, I knew to set them equal to each other because I know they have a point of intersection, and that is when the two lines are equivalent. So that's why I knew to set what y equals in the top equation to what y equals in the bottom equation. All right, so I'm probably going to want to go ahead and combine my x's. I'm going to do the inverse of a negative 2x, so I'm going to add 2x to both sides. Because remember, whatever I do to the left, I must also do to the right to balance my equation, right? When doing so, I get a zero pair on the right. On the left, 3x and 2x give me 5x. So I have 5x plus 5 equals 20. And then I'm going to go ahead and subtract 5. So I'm going to bring over this positive 5 or plus 5 to the opposite side. I get my zero pair on the left. On the right, I do 20 minus 5, and I get 15. And last but not least, we're going to divide by 5 to solve for x. And 15 divided by 5 is 3. So we're partially done with system A. We have found that x is 3, but we also need a y solution because we know the solution to a system has to be a coordinate, an ordered pair, a point of intersection, right? So how are we going to go back and find y? Well, here's where you can choose either equation from the original system. If you'd like to use the top equation from the system, you very well can. If you'd like to use the bottom equation from the system, you very well can as well. I'm going to go ahead and choose the top equation in the system just because it's all positives. Might make my life a little easier, so why not? So I'm going to use y equals 3x plus 5, and I'm going to replace what I got for x into that equation in place of x. I got 3, so I'm going to replace it with 3. And then I'm just going to complete the math. 3 times 3 is 9. And 9 times 5, or excuse me, 9 plus 5 is 14. So now I have an x value to my system and a y value. So when x is 3, y is 14, and that should be the coordinate that holds true for both equations in the system. Now here's where we can utilize the graph to check our work. The point of intersection for graph A should be located at point 3, 14. Does that appear to be true? Well, if I go right approximately 3 and up approximately 14, there we have it. So we had to use the algebraic method to get our solution because these graphs are not very clear, especially since they're counting by 5s. We would have definitely had an estimation, which would be close, but we want that exact intersection point because that gives us our exact solution to the system at 3, 14. All right, so now that you've seen and you've done problem A with me, why don't you go ahead and pause the video and see if you can attempt to solve system B and then check your work with mine. All right, so I am going to erase this. You can obviously go back in the video if you need to rewrite anything. And I'm going to go ahead and work through system B. So check your work and your answers with mine. So just as we did system A together, I am going to take the top equation and what it's equal to, 2x minus 10. And set it equal to what y equals in the bottom equation, which is 4x minus 1. And I am going to go ahead and solve this equation again in terms of x. So maybe I'd like to move my 2x over to the right by subtracting 2x from both sides. And the only reason I chose to move the 2x is so over on the right I'd be dealing with positive x's, but you could have moved the 4x first as well. I got a 0 pair on the left, so I have negative 10. 4x minus 2x gives me 2x on the right, minus 1. Then I'm going to go ahead and add 1 to both sides to balance the equation and to eliminate my minus 1 from the right. And I get negative 10 plus 1, which is negative 9, equals 2x. And then last but not least, to solve for x, I need to divide by 2. And I get, when I divide negative 9 by 2, I get negative 4.5 for x. So now I have a solution for x, negative 4.5 or negative 4.5. I need to use that solution to find y. So again, you can go back to the system of equations. You can choose. Do you want to use the top equation or the bottom equation and replace x with negative 4.5? It's not going to make a difference. In this problem, let's go ahead and test it in the bottom equation. So y equals 4x minus 1. So I'm going to go ahead and replace x with our negative 4.5. So I have y equals 4 times negative 4.5 minus 1. All right, so let's go ahead and do the math. If you need to grab a calculator, please do. So we're doing 4 times negative 4.5, and we get negative 18 minus 1. And when I do negative 18 minus 1, I get negative 19. So now I have a solution for my y value. When my x is negative 4.5, my y is negative 19. So when I go to graph C, that should tell me the point of intersection should be at negative 4.5, comma, negative 19. So again, let's make sure that that matches up with our third graph. If I go left approximately 4.5 and down approximately 19, we are there. Okay. There is our solution, that point of intersection on graph C. Again, we couldn't use the graph to find the exact solution because of the estimation and the scaling of the 5. So therefore, the algebraic method that we just utilized helped us get that exact solution for graph C. All right, make sure you have all the required work, and let's go ahead and dive into the third system on the page here, and make sure that it truly does match up with graph B. So using the same approach as the other two, I'm going to take what y equals in the top equation, so that's 0.5x plus 12, and set it equal to what y equals in the bottom equation, which is 2x plus 27, and start solving our equation for x. I think I'm going to go ahead and move the 0.5x over to the right side, so I'm going to do the inverse of a positive 0.5x, which is a negative, or subtracting. Oops, let me fix that. Subtracting 0.5x from both sides. So whatever I do to the left, I have to do to the right. So minus my 0.5x plus 27. All right, so on the left we get our 0 pair, left with 12. On the right, 2x minus 0.5x gives us 1.5x plus 27. Okay, then we can go ahead and move our 27 from the right to the left and do the inverse, which would be subtracting 27 from both sides. 0 pair on the right. 12 minus 27. If you need to grab your calculator, go ahead and do so. We should get negative 15 equals 1.5x. And finally, to solve for x, divide both sides by 1.5. Again, grab that calculator. Negative 15 divided by 1.5 gives me negative 10. All right, so I have an x value here. And now I need to go back and find my y value to the system algebraically. Again, remember, the choice is yours. You can choose either the top equation to input negative 10 into or the bottom. I'm going to choose the bottom equation just because it doesn't have the decimal, so it's going to be a little bit easier for me to work with. Definitely you can choose the top if you prefer though. So I'm going to choose my y equals 2x plus 27. I'm going to take what I got for x and input it into the equation. So negative 10 replaces x. And then I'm going to do the math. 2 times negative 10 gives me negative 20. Negative 20 plus 27 should give us 7. So now we have a y value in our system for our solution. And let's double check that on graph B, that the point of intersection should be about negative 10, 7 when we use graph B. So let's have a look. So if I go left 10, up approximately 7, there we go. There we have our point of intersection. So we are confirmed that graph B does in fact match system C, or the third system. And we proved that algebraically here. All right, so please make sure you have all this work in your workbooks. I know it is a lot of work, however, it's very important. So we've now learned and realized there are 2 ways to solve systems, both graphically and algebraically. Sometimes the graphic method is not the best method in all cases, especially in this one, because we were getting estimates as opposed to solving it algebraically with the equations where we get those exact solutions or points of intersection. All right, so if we recap a couple of things, do you need to see the graphs and the equations in order to, that says solve under there, in order to solve the system? And the answer to that, we just said, is no. You don't have to see the graphs. They are helpful, but you don't always have to. We just learned that you can solve systems algebraically. So you can solve algebraically using the equations. How do you know your solution doesn't contain any errors? Well, that's the nice thing about checking it with the graph. Your solution, your ordered pair solution by solving algebraically, should be equivalent to the point of intersection on the graph. So you can use the graph to check and make sure the 2 coordinates, the 2 points, are the same. How does solving the systems of equations compare to solving equations with variables on both sides like we did in earlier lessons? Well, to find the x value of our system of equations, it's the exact same concept as solving an equation like we did earlier in this unit. You have two original equations in the system that we were able to make one giant equation out of by setting them equal to each other. And then you still use inverse operations to solve for x, just like you're used to doing. So you're still using inverse operations to solve for x. The new piece here is that you now also have to go back and find y. So you have to choose one of those original equations to substitute x in for and find your y value. So that's really the only new piece that's different from what we did earlier in the unit. When you solve the equations with variables on both sides, some had one solution, some had no solutions, and some had infinitely many solutions. Do you think systems of equations can have no solutions or infinite solutions? Well, in previous lessons, we've already learned that systems can have no solutions, right? When we saw it on a graph, what did that look like? Well, that was two parallel lines, right? When the lines intersected, we learned that that represents one solution to a system. So, could they have infinite solutions? Well, we did actually see this in one of our previous lessons as well. If you recall, it ended up being both of the graphs. Sorry, my calibration is not perfect as usual. Being graphed on top of each other, we referred to that as coinciding lines, right? When the two fall on top of one another. So that should appear when we're working with things algebraically as well. So we're going to see what that looks like. We've seen it graphically. What might that look like algebraically? Well, in fact, you did see that earlier in some earlier lessons in this unit. Remember when they have no solution, we got two unequivalent numbers in the end. And if they had infinite solutions, we got the exact same two numbers that were equal to each other in the end. So look for those patterns with systems as well. They're very closely related. All right, so let's go ahead and dive into the second activity, different types of systems. So here it says, remember when you sorted equations with single variables where each equation had either one solution, no solution, or infinitely many solutions, which we just talked about. Just like one variable equations, systems of equations can also have one solution, no solution, or infinitely many. What do you think the graph of the equations from systems with no or infinitely many might look like? Let's record our possibilities here. So we briefly touched upon that on the last slide. So let's go ahead and jot that information down. Shoot, you don't have much room in your workbooks, do you? Actually, at the top of page 71, question 2 does address this. Describe what the graph of a system of equations looks like when it has one solution, zero solutions, and infinitely many solutions. So we will get there. So we'll do that next. All right, so with the next activity, you're going to go ahead and take out the handout that you grabbed when you walked in the door from the tray today. And your task for this activity is to graph each system carefully on the provided coordinate plane. Then check your work with mine. So if you want to graph one, like press pause on the video now, graph one, check it with mine, and then fix your work, press pause, graph the second one, check it with mine. So that might be the best bet to go. So let's go ahead and do that. So go ahead and pause the video now, try the first system, and then check with mine. Okay, so when we graph system A, it's telling us that it should have a solution. So if we were to graph this, we probably want to put them both into slope-intercept form first to make our lives a little bit easier. So I'm going to go ahead and do that, or let's do that together if you haven't done so already. And I'm going to do so by distributing. So when I distribute the -4, my top equation is -4x. And a negative times a negative makes a +8. Okay? So let's go ahead and graph that equation on our coordinate plane. So the initial value is 8, so that tells me to start at 8 on the y-axis. So 5, 6, 7, 8. Plot your point. Excuse me. From there, my slope tells me to go down 4 over 1. So I'm going to go down 1, 2, 3, 4 lines over 1. And continue that pattern down 1, 2, 3, 4 lines over 1. Down 1, 2, 3, 4 lines over 1. Okay, grab your straight edge. Okay, and connect your points for your first line. Remember, they go on forever. Hopefully yours is much straighter than mine on the smartboard. I know it's hard for me, but hopefully you have your straight edges, your rulers, so yours should be much straighter. All right, let's go ahead and graph the second equation. I'm going to encourage you to use a different color. So if you want to pick out a colored pencil, might not be a bad idea, and graph your second one in another color so you can clearly see. I'm going to do my second one in blue. Okay, so I'm going to go ahead and distribute, again, just like I did with the top equation in the system. I'm going to distribute the -2, so I have -2x. And -2 times -5 halves, remember, a negative times a negative makes a positive. And 2 times 5 halves, the 2's cancel out, and I'm just left with 5. So that tells me my y-intercept is at 5. And from there, I am going down 2 over 1, 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 okay, and so on and so forth. You're going to use your straight edge to connect yours. Again, yours should be so much more clear, hopefully, than mine, okay? And when you do this, we do get one solution, right? We get one solution, and we need to identify that point of intersection. So as you can tell from my graph, it's really hard for me to tell because I didn't have a straight edge, and my graph may not be as clear. So hopefully your graph is clearer and you can identify your point of intersection. But what Mrs. Simmons could do is I could solve it algebraically to confirm that where that point of intersection is. Because if I estimate on mine, it appears to be somewhere around 1.5-ish, comma, up to 1.5-ish. So I'm going to go ahead and I'm going to solve mine algebraically. So that was, oops, I'm going to set them equal and see if we get that same point of intersection. So that was -2x plus 5. So if I go ahead and bring my -4x over and I add -4x to -2x, I'm sorry, I'm going to add 4x. Yeah, so -2x plus 4x gives me 2x plus 5 equals 8. I'm going to bring my 5 over to the right and subtract it from 8. So I'm just not showing all my steps right now since I'm trying to do this a little quicker to match up with your guys' graph. And 8 minus 5 gives me 3. And then if I divide both sides by 2, I do in fact get 3/2, which is equivalent to 1.5, right? And then when I go back and substitute that into either equation, I'm going to go ahead and use the blue one here. So y equals -2 times 1.5 plus 5. -2 times 1.5 gives us -3 plus 5, which is 2. So the solution is at 1.5, 2. So hopefully your graph clearly shows that, but like I said, since I had to estimate with mine, with my not having my straight edge. But yeah, we can see that if I go right 1.5 up to, there is our point of intersection. Glorious. All right, so equation B is also telling us this has one solution. So we're going to go ahead and try this right now. This is so fucking long. Solution here. Okay, so this is for the D. Okay, sorry about that. For that pause in time there, I was working some math out. Didn't realize that I was still recording. I thought I had hit pause. Okay, sorry about that interruption as well. All right, so if we, for time's sake, it also tells us that equation B is going to have one solution. So I'm not going to go through it with you, but you can check your work with me. The point of intersection should be at 3, 0. So if you graphed your lines, that should be where the two lines intersect. So let's go ahead and move forward to system C, which they're telling us system C has no solutions. So let's prove why system C has no solutions, both graphically, and then we can talk about it algebraically in the system why that holds true. So if I were to go ahead and graph the top equation, which is already put in the slope-intercept for me, I'm going to start at 3 on the y-intercept. So 1, 2, 3, and my slope tells me to go up 2, 1, 2, over 1, up 2, over 1, up 2, over 1, keep going, up 2, over 1. And connect. Okay, and again, you're using a straight edge, your line's going to be a lot nicer and clearer and straighter. Then I'm going to go ahead and graph my second equation, which again is already in slope-to-intercept form for me, and I'm going to start from -5 on the y-axis, since that's our y-intercept, and from there again I'm going to go up 2 over 1, up 2 over 1. Okay, you're doing the same, up 2 over 1. Hopefully we're noticing, and again, yours are much clearer, neater, straighter, that these are what types of lines? These are parallel lines. Therefore, they will never intersect. They will never touch each other, so that is why they have no solution. An indicator in our equations that I can see right away that also indicates that they're going to have no solution is that they have the same slopes, but they have different y-intercepts. So when this occurs, that's going to result in a no solution. Okay, so if you were to set the two equal to each other, you'd essentially, your two x's would cancel out and you'd be left with 3 equals -5, which we know is not a true statement. So that further proves why this system has no solution set. All right, so let's go ahead and try D. D is a little bit more complex. They're telling us it has no solutions, but the second equation is not in slope-intercept form. So let's put it in the slope-intercept form. So let's first distribute the -5. So I have y equals -5x, and negative times a negative is a positive 10. Minus x, then I can go ahead and combine my x terms. So -5x and -x give me -6x. Now I can see, here's my equation. I can go ahead and graph that. So I'm going to start at 10, and I'm going to go down 6 over 1, down 1, 2, 3, 4, 5, 6 over 1. Okay, so on and so forth. Again, your line should hopefully be much straighter than mine. I'm going to graph the top equation in blue. I'm going to start from my y-intercept, which is nothing, so that means 0, and go down 6 over 1, down 6 over 1. And we are seeing, again, those parallel lines, which is an indication of no solution set. When we condensed the second equation, notice our slopes. Negative 6x, negative 6x, exactly the same. And notice our y-intercepts, 0 and 10. Different y-intercepts, same slopes, resulting in parallel lines. Let's go ahead on to equation E. They're telling us with equation E that this should have infinite solutions. By just looking at the equations in the system, I can't tell because the top equation is not in slope-intercept form, but the bottom one is. So let's do some rearranging here to the top equation so we can get it into slope-intercept form. So I'm going to distribute my 3. So now I have 3 times 2x, which is 6x. 3 times 1 gives me 3 minus 4x. Then I'm going to go ahead and combine my x terms. So 6x minus 4x gives me 2x plus 3. Let's take a look at both of these equations. 2x plus 3, y equals, and again up here, y equals 2x plus 3. So if I graph the top one in blue, I start at 3, 1, 2, 3 on the y-axis, and I go down 2 over 1, down 2 over 1, down 2 over 1. Okay, I draw in my line. And when I graph the bottom equation that we rearranged into slope-intercept form, I again start at 3, go down 2 over 1, down 2 over 1. We're seeing it's the same exact line, or like we said the other day, these lines coincide. They fall right on top of each other. So therefore, that's an indication of infinite solutions. So you can go ahead and we're actually going to, since this lesson is quite lengthy, we're going to skip that empty box. Originally that empty box below was going to ask you to create your own system of equations and graph it and determine how many solutions it would have. Did you create a system with one solution, no solution, or infinite solutions? If you have time and you'd like to do that, that's awesome, and you can turn it in to me tomorrow for extra bonus points, and I will definitely take a look at that. All right, so some things to recap. And you can go ahead and actually recap this on page 71 in your notes. Let's backtrack there and fill that in where it says question 2. Describe what the graph of a system of equation looks like when it has one solution. We have a point of intersection, so fill that in. Okay, 0 solutions. Our graph has parallel lines. And infinitely many solutions results in a graph with coinciding lines. Meaning the lines are exactly the same, right on top of one another. So those are huge visually in the world of systems of equations. So if there's one solution, we'll have 2 lines that intersect. 0 solutions will result in parallel lines, and infinitely many solutions will result in coinciding lines, or the same exact lines. All right. So those are the main highlights. You can absolutely please go through, read your lesson synthesis. Always important, good stuff in here. They go ahead and, talk about that a little bit more in the lesson synthesis, and they even, in your summary, get into solving algebraically, and they give you that example of like how we solved many in today's lesson algebraically by setting the 2 equal to one another, okay, and then going back and finding the y value. So by setting them equal to each other, you do the math, you get the x value, and then you choose either of the original equations. So if they chose the first equation in the system or the second equation in the system, they should still result in the same output for y. So we can check that work by completing this math for them. 2 times -2 is -4, plus 6 gives us 2. Or if you check it in the second equation replace x with -2, Negative 3 times negative 2 is positive 6. 6 minus 4 is 2. So they're just proving how either equation will work and get you the y value you need. So in this system, in your lesson summary, the solution would be when x is negative 2, y is 2. So this is an indication of one solution, and our lines would intersect at that exact point. All right, and they show us that even further. Okay, and they show you the graph in your lesson summary. You can see that point of intersection. Beautiful, it matches up. So just to recap, no solutions, the lines would never intersect, they would be parallel. Exactly one solution, our lines correspond to each other and intersect exactly at one point. And an infinite number of solutions, the graph of the two equations are the same line, otherwise known as coinciding lines. All right, go ahead and use the remainder of class to work on your lesson 13 cool down. And as soon as you are done with this cool down, please put it in the inbox and have a wonderful day.